What the heck?
Tagon.
Okay, so today we're going to be solving quite an interesting little geometry problem. We have ourselves a quadrilateral ABCD that is a unit square. It is a square with side length 1. And you will notice that triangles ABI, DEF, and GHI are all inside the square. They are all equilateral triangles. And in particular, ABI shares the base of the square. So it is an equilateral triangle where all three sides are equal to 1. Triangle DEF is an equilateral triangle defined as such. It is tucked up against the blue triangle, and its top base is up against and parallel to the top of the square, and one of its corners is tucked up in the corner of the square. So that sort of defines this to be one and only one equilateral triangle. Likewise, GHI is also tucked up against the blue triangle, except now one of its corners matches up with the top corner of the big blue triangle, and then its top face is parallel to the top and bottom of the square. And so the question we want to solve is precisely how far apart are the points G and E? How long exactly is this dotted line? You may have noticed this post on my Instagram account, posing the same challenge to people, and I believe only a couple of people were able to get it, and I think they did it on my community post on the YouTube channel, actually. But I did post this to my Instagram account. And the tactic that we're going to use to solve for this length here is actually quite simple. You just need to know a little bit of trigonometry. And the method is going to be to find out this side, this angle, and this side of this triangle in here, GIE. And then we can use the law of cosines to find the missing side there. And so it should be pretty easy. Notice these points are almost the same height inside the square. They are not quite aligned, to create a line segment that's parallel with the base. So this line segment is not parallel with the base, but it's only just off. So we should expect that this length should be pretty close to this length here, whatever this length is. And as it turns out, the side length of the orange equilateral triangle is precisely 1/2, because we can see that the top base is both parallel to the base, and it extends from the edge of the square to the vertex of the equilateral triangle in the middle. That is sort of, it's not inscribed in the square, but it shares a base of the square. And when you drop a vertical in an equilateral triangle, you bisect the opposite side. So we definitely know for certain that this is 1/2 in length, because it goes from the edge to the vertex of the big blue triangle. So if any side of this, I guess it's brown, not orange, but brown equilateral triangle is 1/2, then all of the sides are. So we know for certain that GI equals 1/2. That's very helpful. So GI equals 1/2, and because it's equilateral, we know that all three of these sides are 1/2. We know that all three of the sides of the blue triangle are 1. That's a given. Now, how would we go about finding the side lengths of the pink triangle? Well, I'm just going to rewrite the point E down here, just so I have more room. You'll notice that I can, again, drop vertical here, because this is an equilateral triangle, so this angle is 60 degrees, which means the angle in here, the complement to it, since this is a right angle, this is 30 degrees, or pi/6 radians. Likewise, this is also an equilateral triangle, so this angle, too, is pi/6 radians. So those two angles are congruent. Because they are congruent, that means that these two lengths must be the same, because that's an isosceles triangle, which means if I dropped this vertical here, thus intersecting the side AD at a right angle, that would cut these two sides, this side directly in half, which means this length here, from D to the middle of the side, is 1/2. Since this is pi/6 to go from here to here, since this is a 30, 60, 90 triangle, I simply have to divide this length by the square root of 3. So if I call this point J, right, then we're saying DJ is 1/2. And that means that EJ is 1/2 times the square root of 3, because this is the short leg of a 30, 60, 90 triangle, and the long leg is root 3 times longer. So to go from the long leg to the short leg, we have to divide by the square root of 3. then of course to go from the short leg to the hypotenuse, we simply have to multiply by 2, which means that the side lengths of the pink equilateral triangle are just 2 times this quantity here, or 1 over the square root of 3. So we know that the side length, df, is 1 over the square root of 3. Also known as root 3. So we have the side length of the pink triangle, but what we want really is EI, which is just a bit shy of EF there. And how we're going to do that is we're going to sort of compare similar triangles. So I'm just going to rewrite I up here to label this the tippy top of the blue triangle. And what I'm going to do is I'm going to continue this parallel line across to the other side. And what we're going to do is we're going to drop a vertical inside the pink triangle, which means this is a right angle and this is a right angle. And since this is 60 degrees, this is 60 degrees, and this is 60 degrees, our little triangle here, that's sort of the base being this dotted purple line, is going to be similar to all of the other equilateral triangles. So we want to find this gap here, because we want to see what we have to do to get from the pink triangle to the smaller pink triangle. In fact, I'm going to draw another pink line there to signify that this is just sort of a smaller pink triangle. Like so. Oh, that's not really that parallel. Let's try that again. It's better. Not really. But okay. Point is, we want to find this distance here. The distance between the top of the square and how high the blue triangle is. Well, that's not too hard. Since this angle in here is pi over 3, if we were to drop a vertical inside the big blue equilateral triangle, then with a hypotenuse of 1, that would make a right triangle. And the sine of pi over 3 is root 3 over 2, and so the height of the blue triangle is the square root of 3 over 2, which means that the gap between the top of the square and the tip of the blue triangle is 1 minus the square root of 3 over 2. So CH is precisely 1 minus the square root of 3 over 2. Which means that the height of this new pink triangle is 1/2 minus the quantity 1 minus root 3 over 2, because we're simply starting with 1/2 and taking away this amount, which means the height of this pink triangle here is precisely 1/2 minus 1 minus root 3 over 2. Distributing the negative and combining like-ish terms, we end up with square root of 3 minus 1 over 2 is the height of this triangle here. But we don't want the height of this triangle. We don't want the short leg of the triangle. We want of this right triangle here. We want the hypotenuse of that right triangle there, which is this, and therefore the second side of the triangle we're trying to find, which is namely GEI. And so to get there, we have the long leg of this right triangle, which is 3 minus 1 over root 2. We have to divide by the square root of 3 to get the short leg, and then we have to multiply by the square root of 2 to get the hypotenuse. So if we just multiply this by 2, so we're going to do root 3 over minus 1 over 2 times 2 over the square root of 3. The 2's will cancel, and I'll be left with root 3 minus 1 over root 3, but what we're really going to want to do is rationalize that, so we'll multiply by square root of 3 over root 3 again, just to rationalize. So we get 3 in the denominator, we distribute the root 3, and now we have that IE, the all-important missing side, is precisely 3 minus the square root of 3 over 3. Right? We just worked that out. We also know that since ABI is an equilateral triangle, this angle in here is precisely pi over 3. Now we have GI, and actually no, I did mean GI. GE is what we're looking for, sorry. GE is the fundamental question, how long is GE? Sorry, my mistake, GI is 1/2. This right here, GI is 1/2. We know that IE is 3 minus root 3 all over 3, and we know that the angle between them is pi over 3. So those are the important lengths we have now. Now we just need to recall something called the Law of Cosines. So if I call this opposite side GE, if I call that, well, we'll just call it GE, it doesn't really matter. So I'm going to erase the values now, and we're just going to rewrite them after we talk about the law of cosines. So here's a link to the law of cosines video that I made proving that result, so I will just be stating it here. If you have a triangle with side lengths A, B, C, and an angle theta between A and B, then it is true that C squared equals A squared plus B squared minus 2AB times the cosine of theta. And this is just a generalization of the Pythagorean theorem, because if theta is 90 degrees, or pi over 2 radians, cosine of that is 0, and that term goes away, and you are simply left with the Pythagorean theorem. So that's nice. But how do we use that to solve this problem? Well, C in this case is GE, A is GI, B is EI, and theta is the angle GIE. So we can plug all of those things into the equation, take the square root of both sides, and we'll have our answer GE. So let's fill in the values. So we know that, well, I can erase the formula now. We know that GE squared, the length of that squared, so GE squared, is equal to 1/2 squared, because that's the length of GI, plus the length of IE, which is 3 minus the square root of 3 over 3, all squared, and then it's minus 2 times GI, which is 1/2, times IE, which is again 3 minus the square root of 3 over 3, times the cosine of pi over 3. Now we can do some drastic simplifications. 1/2 squared is 1 over 4. We can just FOIL this out, so we're going to end up with 3 squared, which is 9, plus root 3 squared, which is 3, minus 2 times 3 times root 3, so minus 6 times the square root of 3, over 3 squared, which is 9. Negative 2 times 1/2, 2 times 1/2 is just 1, cosine of pi over 3 is again 1/2, so we're going to get minus 1/2 times 3 minus root 3 over 3, so we're going to get minus 3 minus root 3 over 6, because the 2 and the 1/2 make 1 when you multiply them together. Now I want to find a common denominator to combine all of these things together, and that's of course going to be 36 as the smallest number that 4, 9, and 6 go into. So if I want this to be 36, I need to multiply the top and bottom by 9. So I get 9 over 36. And then here I want to multiply the tops and bottoms by 4, because 9 times 4 is 36. So I'm just going to combine like terms. I have 12 minus 6 root 3 on top, so if I multiply the top and bottom by 4, I get 48 minus 24 root 3 over 36. And now I multiply the top and bottom of this by 6 to get 36, so I have minus 18 minus 6 root 3 over 36, which of course comes out to 9 plus 48, which is 57, minus 18 is 39, negative 24 root 3 minus negative 6 root 3, which is minus 18 root 3. And that is GE squared. So to get the final answer, we simply have to take the square root of both sides, and we get our final answer that GE is precisely the square root of 39 minus 18 root 3 all over the square root of 36, which is of course just 6. And as I said, this was going to be a little bit less than whatever the length of the side length of the orange triangle is. We discovered that the side lengths of the orange triangle is 1/2, and it turns out that this is ever so slightly less, and it's about 0.466. So our inference is confirmed by the answer. So it is precisely the square root of the quantity 39 minus 18 root 3 all over 6. Thank you very much for watching. Toodaloo.